All right, so we're going to look at what's known as trig substitution today. So trig substitution is just like regular substitution, except we're going to be substituting in trig equations. So the nice thing about when we're looking at any kind of U substitution, we can, in essence, make U anything we want. The key, though, is when we do that, we have to do the derivative piece for the dx. So it's almost like taking an equation and adding 5 and subtracting 5. You're basically balancing it out. So that allows us to make U anything we want, which is kind of a nice little thing. So if we look at this equation right here, so actually, we'll do this. If we look at, that's what I wanted to do. So we have the equation, let's do 4 minus plus x squared dx. So we've got that. Now, if I was going to do U substitution on this, I would probably take it and make the middle part my U. So I could say U is 4 plus x squared. So then I have to do du would be 2x dx.
Professor, couldn't we just put a 4 to the 1/2 and kind of split it out?
So hold on, let me. So you want to do this? That?
Right.
Can't do that. You can't.
Oh, because they're now multiplying.
Right.
Okay.
Exactly. Yes. Can't do that. Good question. Good little note. Yeah, you can't split up. It's the same concept of like if you have things in parentheses with the squared, you actually have to FOIL it. You can't just split them up and just square each of the pieces. So when we're doing the du, notice I've got a 2x here. I don't have an x in my integral. Since I don't have an x in my integral, I can't really do just a simple U substitution for this because I need something for the du. And if because we can pull over numbers. So let's say, all right, let's do this. Let's do 1 over 2x du equals dx. So if I did the substitution, I'd have the square root of u, and then I'd have 1 over 2x du. Now I have an x and a u in my problem. So we're still kind of stuck. So because these problems come up, especially when we're dealing with circles and ellipses and things like that, we needed a way to be able to do the integral of these. And that's where the trig substitution comes into play. So trig substitution says that if I take the u and make it that piece inside, my du is going to have to be some other part. So I'm going to actually make it, instead of substituting in a u, I'm going to change and make the x a sine theta or another trig function. So if we look at that in terms of this, so let's actually do this one out. So we have, we're going to set x equal to a sine theta. And we're working with this. So what I'm going to do now is I'm going to say x is that. So now I have a squared minus a sine theta squared. I'm not dealing with the du or anything else, the dx and stuff like that yet. We're just looking at the square root to figure out why this would actually be helpful. So if I take this now, I can split up my square, the square. So I have a squared minus a squared sine theta, or sine squared theta. So the next step, I can factor out my a squared. So now I have 1 minus sine squared theta. So now I've taken something that was, in this case, subtraction, and made it into something that is multiplication. So I can't remember who said it. You wanted to split up the square root. Now I can split up my square root. So I can split up my square root to the square root of a squared and the square root of 1 minus sine squared theta. So that's just a. But I've got this piece over here. I still got subtraction. However, remember, we have a Pythagorean identity. If I was to move the sign over, this piece in here would be cosine squared theta. So now I can take the square root of that. So I've now gotten rid of my square root.
Professor,
Yes.
I follow everything that you did once you had square root a squared minus x squared, but how do we go from x equals a sine theta to square root of a squared minus x squared?
Oh, no. So this was my original problem.
Oh, okay. Yeah, the x
That was
equals
my
a
original
sine
problem.
theta threw me up.
And I'm substituting, I'm changing x to a sine theta.
I see.
So, and the goal is basically to get rid of that square root so I can actually do the integration. So, like I said, we didn't do the integral in this piece. I haven't done the dx and everything else in there, but you can start to see how this would make that square root a lot easier to work with.
So, Professor, for my understanding for how it applies to like the problem we're doing, are we gonna take like the 4 and make it 2 squared to make it come the same thing how a is, or is it complete? Am I just
Yeah.
off the?
Yeah. So if there's a number like in the one we were doing here, where I had the 4, my a would be 2. Yes.
Okay, that makes sense. Then I was just trying to figure out how it related.
Yeah.
So where does the logic come in here, like Professor, where are we effectively saying that any number, any real number can be represented by a value of sine theta multiplied by a?
Yes. However, you got to remember, whenever you do something in these problems, you have to balance things out. So I didn't do that in this problem. I changed what x was, but I didn't balance it or anything else. So, but in essence, yeah, I can basically create any single number from a sine theta. Because remember, sine is basically every number between -1 and +1, right? And if I multiply that by any other number, I can get any number you would possibly want. So yes, in essence, I can represent any number as a sine theta.
Interesting.
So, and then the balance piece is where the dx comes into play, and having that part replaced with the theta, so you can actually have the, so this way you're adding and subtracting, so you're not actually changing the actual problem, you're just substituting.
So the final pre-integral, well, I guess we haven't done that yet. We're gonna do it now.
Yeah, so, well, I'm going to do it in actual, we're doing an actual problem. So in essence, this would be there, and then I would have the d theta part at the end that I'd still have to work with. But I'm going to actually do it with a regular problem so that we don't have a whole bunch of extra letters in here. That will be end up confusing. So, but let me get you the table first, because this is actually really important and helpful. Here. So there's only 3 ways that I can write my square root. Okay, I can write it as a squared minus x squared. I can write it as a squared plus x squared, which also would be x squared plus a squared, depending on the direction, because addition can be switched. Or x squared minus a squared. Those are the only 3 ways we can do it. And you can see here, they give you what your substitution is going to be. So the first one, x will be a sine theta. The second one, x will be a tangent theta. And the last one will be x equals a secant theta. So that's going to be our substitution. That's what's going to be able to solve this problem and make it easier for me to work with.
That second part of the statement is telling us the interval in which this is true.
Yeah, so because remember, sines and cosines and stuff like that, or tangents and all, they repeat. So you want to look at a very specific domain so that it actually is a function and it only happens once. Because one of the things that we're going to do when we solve these problems is, remember, whenever we do a substitution, I have to go back to my original problem. So if I'm substituting in a sine theta, my final answer still has to be in terms of x. So I've got to be able to change it back. So we need that one-to-one function there. So between negative pi over 2 and pi over 2, sine is every single value from negative 1 to 1, but it doesn't repeat itself. So it's a function either direction. That honestly comes into very little play though. So this part here, it's here for your information, but it doesn't really come into play when we're doing a lot of the calculations.
Okay.
All right, let's look at one. All right. So first thing, look at the problem and see, can I do just a simple U substitution? You always want to look at that as a possibility, because if you can, it makes your life easier. So in this problem, I cannot, because I don't end up having, I have x squared would be left over, and I'd only have an x left over. So that would not work. So I have to do my trig substitution. So the first thing we want to look at is, what am I going to set my x to? So this one is 9 minus x squared. So I'm going to set my x to 3 sine theta. Okay. And that goes back to, because a squared is 9, so a is 9. The next thing we need is I need my dx. So I'm going to do the derivative of 3 sine theta. The derivative of that is 3 cosine theta d theta.
Do we now solve for d theta, or it's already at
Nope.
dx?
Because we're replacing the dx. So I don't need to solve for d theta. So, and other problems when we were, when we had the du, the dx was on the other side. I had to solve to get the dx by itself. In this case, my dx is already by itself. So we're actually replacing dx. So instead of replacing something with dx with u, I'm actually replacing this whole thing. That whole part's going to go in there as the dx.
So I'm sorry, I still don't understand. When do you solve for the dx? Like when we did for du, we would solve for dx.
All right, hold on. I'll show you. So let's just take a really simple equation. We'll keep the same concept that we're doing. So I'm going to set u to be 4 minus x squared. So du is now 2x dx, right?
Yep.
Okay. I don't have, so here I've got x and dx. So I've got that. That's what I want to replace in this situation. So that's where I'm going to divide both sides by the 2. So I have 1/2 du equals x dx. So that's what I'm replacing with the 1/2 du.
Mm-hmm.
Okay, does that make sense?
Yep.
Okay, so now in this problem that we're looking at, Same concept. I've got a dx there. I'm looking at what I'm replacing the dx with. In this case, I'm replacing the dx with 3 cosine theta d theta.
Because there's no extra,
There's nothing else next to the dx.
well, couldn't technically, isn't technically there a 1 over x squared?
No, because I'm actually, well, yes, there is a 1 over x squared, but I've not even dealt with that yet. I'm literally I'm replacing x, so that x squared doesn't actually exist anymore.
Oh, right. Okay.
So that's the next thing I was actually going to rewrite this. So right now I've got 9 minus 3 sine theta squared over 3 sine theta squared. Oh, hold on. I'm going to run out of room, so 9 minus 3 sine theta squared over 3 sine theta squared, and this becomes 3 cosine theta d theta. That's my new problem. And now everybody's looking at that problem going, that problem is a heck of a lot harder than the first problem we looked at. And yes, you'd be correct.
So when we
Alright, so
chose
now-
to replace,
Scott,
when we chose to designate x as 3 sine of theta, you chose that because we're looking at a problem that met the a squared minus x squared from the table.
correct.
So what you're looking at there is that ax?
Yeah, because A is sine. I mean, sorry, A is 3,
Yep.
because that's from the 9 squared. Because remember, that would be the a squared minus x squared. So in this case, a equals 3. So that's how I get the 3 sine theta. Because a squared was 9.
And x squared becomes sine of theta because it just fits with the table. We just take the table for what it's worth.
Correct.
Okay.
You're going to see why it makes sense in a second. Because like I said, when you're looking at this, this looks a lot more complicated than my original problem. But the reason we do it is because when we're looking at these problems, we're now going to be able to simplify this problem down and break some stuff out and solve it and make it simpler to work with. So that's the next piece that we have to do. So let's look at the top first. So what I would typically do is I simplify my problems down in pieces. I take the most complicated part first and simplify it down. So let's take the square root and try to get that as either gone or as simplified as I could get. Okay, so this becomes 9 minus 9 sine squared theta. I can pull out the 9 and I'm left with 1 minus sine squared theta. And then I have 9, and that's cosine squared theta. So this whole thing becomes 3 cosine theta. Does that part make sense? So now my integral that I have is 3 cosine theta over 9 sine squared theta times 3 cosine theta d theta. So I can make this as 9 cosine squared theta over 9 sine squared theta d theta. So you can start seeing how this massively complicated problem that I started with, this thing over here that looks like a mess, once I got rid of the square root, the problem actually becomes quite simple. So this problem, the 9s will cancel out, and I'm left with cotangent squared theta d theta.
And that's from the trig rules, right? For when the cosine over sine squared. That's just how
Yep.
trigonometry. Okay.
Yeah, so if you remember, the easy one to remember, sine over cosine is tangent. So if you flipped it, it's the reciprocal one, which would be cotangent. Now, I don't know the integral of cotangent squared theta, so that's going to be a little difficult to do off the top of my head.
Oh,
However-
what?
I know, right? Drop in the class. He doesn't know anything. Why are we here? All right, but we can change this a little bit. We're going to use one of our Pythagorean identities. So cotangent squared theta is the same as cosecant squared theta minus 1. And that one, I do know the actual integral of it. So the integral of cosecant squared theta is actually negative cotangent squared, or negative cotangent theta. And the integral of 1 is just theta plus 6.
Now we have to go ahead and insert x, right?
Yes. We have to redo this problem. So, but I want to make sure everybody gets to that point and see how I did that part before I totally mess up and get you guys to have to figure out how to actually switch it back. All right, we're good to there. I know, honestly, the hardest part with what's there is you have to remember some of the rules. So, and I think at the beginning of chapter 7, if I remember right. Yeah, right at the beginning of chapter 7, they gave you a bunch of integrals. Those are ones that are going to be used a lot. So they're probably ones you're going to either want to remember or write down, have on your little note card or a cheat sheet to be able to use. The cosecant one's there as well. So that's why we had that one. So I wouldn't worry. I'm not going to do the hyperbolic trig function, so you don't necessarily have to worry about those. But the ones above that one are actually kind of important. All right. So now I have to change theta back to x. So we've got this equation, and I've got what x equals. So I need to change this back. So what I'm going to do is I'm going to divide both sides by 3. So x over 3 equals sine theta. This allows me to draw a right triangle. So we're going to make that theta. What's sine? What was the two sides of a triangle that makes sine?
Over opposite over adjacent.
Nope.
Opposite over hypotenuse.
That's right. Quick, easy way to remember it. If you're teaching, I'm pretty sure you saw this. So sine is opposite of hypotenuse. So it's x over 3. Okay. And I'm going to get the other side is always the original square root function that you started with. So this is going to be 9 minus x squared. Whatever side's missing, it is always the original problem that you have.
Oh, because of the Pythagorean theorem?
Yeah. If you did the Pythagorean theorem out, that's what you'd have left for the other side. But instead of making you do it out every single time, it's just easy to remember that it's literally what you start with.
So why isn't it not 9 minus x squared over x squared?
Because it's just the square root part. It's not the whole problem. Remember, we changed the x to 3 sine theta to deal with that square root part, not the entire problem.
Oh, okay, that makes more sense now.
All right, so now I got to plug back into my problem. So the cotangent is what? Cotangent is, so tangent's opposite over adjacent. So cotangent's adjacent over opposite. So adjacent is square root of 9 minus x squared. Over opposite. Minus sine -1 of x over 3 plus 3. And that's my final answer.
Wow. That's nuts.
This is why there's no way for you to do this problem as that integral. There's just no way you'd actually come up with the right answer. So the question, do you understand how I got the negative square root of 9, that piece for cotangent?
Who knew the Pythagorean theorem would be that important?
You don't necessarily, as long as you have the triangle, you don't need the Pythagorean theorem for it. You just need to remember that cotangent's adjacent over opposite.
But you do have to remember that the hypotenuse is the addition of the opposite and the adjacent, like that 3. So because they're not all equal, obviously.
Right. But that's what I'm saying. So basically, once you get this triangle, you kind of have to do the triangle to get this done. Once you do the triangle, you don't need to do it again in the problem to get that part down. You can use your triangle to figure those things out. But yes, you do kind of need the Pythagorean theorem to do the triangle. You kind of need to remember where things are. So like sine was adjacent, opposite over hypotenuse. So that's why I put that in the opposite, not in the hypotenuse spot.
Do you think realistically a mathematician figuring this out was what got stuck and then realized I could just draw a triangle?
Realistically, I bet you, because I don't know if I've said this in this class, mathematicians are lazy. We hate work. So I guarantee a mathematician sat there, looked at this problem and goes, yeah, I'm not doing it that way. Hey, let's try this. So it's like, I literally, that's what they do. It's like, they could have probably come up with an actual integral that would have come up with the answer for this problem, but why? I got other ways to deal with it. And that's really like, as much as people say math is hard and everything else, that's what math is designed to teach you. It's like trying to teach you how to think about a problem. And if you can't get it at one way, let's find another way to do it. So perfect example, I make a post on Facebook every day calling balance, like that's a variety of different things. Today, I decided to make one about math and finding the an actual problem that we're going to do in a couple weeks. Finding the actual center of gravity of any shape. So I posted, I gave the explanation on it. And then one of my military friends, he was a helicopter pilot. He goes, we just drop a plumb from the helicopter and figure out the balance point to be able to land and stuff like that. And I'm like, yep, that's a perfect example of using math, but not using the math we learned in school. Because they found a solution. They found, he used a plumb bob, basically as a string with a weight on the bottom of it to actually figure out, because it'll always be the center of gravity for the actual object.
Hmm.
So it basically was a simpler solution to the problem so that they didn't have to go through and do all the calculations to find it for the helicopter. So that's what everybody does. That's what a carpenter does with a square. It's like, why do I have to sit there and do the Pythagorean theorem all the time? I have a square. It's like, that's using math as a problem solving method instead of just calculations. So yeah, I guarantee a mathematician sat there and goes, yeah, I'm not going to sit there and do all this extra work. It's like, and then they sat here and goes, why do I have to figure out cotangent? Just draw a triangle and I have my answer. We look at it as, wow, that seems complicated to come up with. But they looked at it as a simpler way to do something that was way complicated the other way. And then the answer looks crazy. So we got that one part. Everybody understand where this came from? The sine -1? So all
That's just because the inverse of to take off a sign, you just put sine -1, right?
correct. Yeah, that's basically, I was gonna say that's basically I just did the sine -1 of this one. So it's sine -1 x/3 equals theta, because they would cancel out on that side. So
So given the ratio, what's the angle that offsetting that ratio?
yep, exactly. That's what the sine negative, that's what the arc sines do. All right, hold on 1 second. I gotta run down and grab my weight something. I will be right back. All right. Look at this one. So we can't do substitution on this one for the same reason we couldn't do it on the last one. The x squared is in the denominator, and I wouldn't have x squared left. So what am I going to set my x to? So we've got, what is it, x squared plus 4. So let's go back to my wonderful table. And we're going to set x to
X plus 2, or, sorry. 2
A is-
tangent theta?
yes. Yep. So 2 tangent theta. So then dx, the derivative of tangent theta is secant squared theta. D theta. All right. So let's make a mess of our problem. So I have 2 tangent theta squared, 2 tangent theta squared plus 4. And then I'm just going to put this up top, 2 secant squared theta d theta. All right. Everybody see that? So now we're going to go through and clean it up. So let's clean up my square root part first. So I have 4 tangent squared theta, 4. 4 tangent squared theta plus 1. So then I have 4, and that's secant squared theta. So I've got 2 secant theta.
So I'm seeing a trend that we have something that's usually common that we can pull out. Is that usually the case?
That's always going to be the case. That's the goal. The goal is to do something that's going to get rid of my square root so I don't have to worry about it anymore.
Right, what I mean to say is like in the last few problems, we saw, you have a 4 that's common that you can pull out in front.
Yeah, you have to. That's actually, you have to have that. And that's the reason why in the process, if you look at the, and actually this is the thing, that's why in front of all these is A. Because when you square it, you're then going to have a squared plus a squared, whatever, with the trig function. So you can always pull out the a squared.
Okay,
That's by design. Because if you couldn't, then you wouldn't be able to get to the identity rule to get the just a single term with the square, which is what you want to get rid of the square root.
gotcha.
All right, so let's look at my simpler trig or integral. So then I have 4 tangent squared theta times 2 secant squared theta. Oh, not squared. Theta. These theta. So I can simplify this down a little bit. I have a 1/4 that I can pull out. And I'm left with secant theta over tangent squared theta. All right.
Wait, I'm sorry. How did you get 1/4? Because it's 2 secant squared theta over 4 tan squared theta times 2 secant theta.
Right.
Oh, it would be 2 over 8. Sorry.
No, that's fine. I figured as you were reading it, you'd pick up where the other 4 came from.
Yeah, yep. I'm
That's fine.
ridiculous too now.
Professor, isn't this all square rooted though? Is it
No.
if you go back to the original problem?
So the square root's gone.
Oh, sorry, I confused the integral for a square root over the entire thing.
Yeah, no, yeah, that's sort of the thing. So yeah, it's just all, that's the thing. You're only typically going to have like that 1 square root, and the goal is to get rid of the square root. That's kind of why we do the trig substitution. So when we plug it in, it's going to eliminate that square root, so I don't have to deal with that part. All right, so here's my problem now. I have this, and I have nowhere to go. So obviously, I'm not going to give you a problem where nowhere to go. So when we're looking at trig functions, if you get to a point where you're stuck, change everything to sines and cosines. Because once we move to sines and cosines, I have ways to be able to manipulate that problem to get it to be simpler to work with. All right. So we're going to take the secant theta over tangent theta squared theta, and we're going to change them all to sines and cosines. So secant is what in terms of sines and cosines?
Cosine over sine?
Nope. So if you think about it, so we've got sine, cosine, and tangent. The reciprocals of those, so sine goes to cosecant, cosine goes to secant, and tangent goes to cotangent. It's all, the letters never match. That's how I remember it. So sine goes to cosecant because sine can't go to secant because it's the same letter.
What's it? 1 over cosine is equal to secant.
Yeah. So that secant is 1 over cosine. And then the tangent squared is on the bottom, so I'm going to flip it over. So it's cosine squared theta over sine squared theta. So this problem simplifies down into cosine theta over sine squared theta. And somebody's gonna sit there, or somebody's sitting there thinking, all right, all I did is actually change secant to cosine and tangent to sine, but I still have something over something squared. And that's not very helpful to me at this point. However, it's actually very helpful because remember sines and cosines constantly switch back and forth when we do the derivatives and the integrals. So sometimes I have to do multiple substitutions. So for this problem, I'm going to make u sine theta, which means du is cosine theta d theta. Notice this right there is that right there. So I have 1/4 the integral of 1 over u squared du. All right, so how many of you have I lost?
Are we gonna use logarithms now?
No, we don't have to use log for this one. If it was just 1 over u, we would. But since it's 1 over u squared, we don't have to. Because I have one I can subtract. So the integral for this actually is just 1/4. And then it's negative 1 over u plus d. And then I can change this back into my, or resubstitute my u back in. So I have negative 1 over 4 sine theta plus d.
And is that our final answer?
Is it in terms of x where I started?
Oh God, no.
Yeah, these problems are long. I'm not going to lie. So my original problem I had, yeah, I'm rewriting something for you, and then I'll switch over. All right, so let's see what we got. So that was my original problem. So I need to get it back to x's. So I'm going to switch this because I really kind of want the things up top, because otherwise it kind of makes it a mess when I'm doing my, when I'm writing fractions. So this would be cosecant theta. So let's make my triangle. Remember my x was tangent, was this one, right? Yeah, 2 tangent theta. So that's theta, that's x. So tangent theta is x over 2. So tangent is my opposite over my adjacent. So this part over here is your x squared plus 4. So what's cosecant? Cosecant is sine, the reverse of sine, or the inverse of sine. So sine is opposite over hypotenuse. So this one would be hypotenuse over opposite. So it's square root of x squared plus 4 over x.
Professor,
Yes.
Wouldn't it not be if, so the hypotenuse, for that triangle, right? If the opposite is x and the adjacent is 2, right? Isn't it x squared Oh, okay. So a squared plus b squared equals c squared. So therefore c needs to be square root. Yeah, right?
Yep.
Sorry.
Oh, no, so don't ever apologize for doing exactly what you just did. Because both of you, when you guys went through and worked through the problem and you actually said it out loud, you actually understood it better and caught the misconception that you had. When you keep trying to do it in your head, or even if I said it, it wouldn't make as much sense and you wouldn't have made the connection as well. So this is why I didn't stop you. This is why I didn't try to explain it. I just let you keep going, because the worst thing that would have happened is you'd have said something wrong and then I would have corrected you. But since you said everything right, I just let you kept going and you figured out, oh, that's why, which is a very good thing to do.
Wait, sir,
That's
I'm
why-
kind of
Yeah,
I'm
go ahead.
having a brain fart moment. So how did it become like -1/4 the x? Like generally, how do we get to like the answer?
Okay, that's fine. So this part right here, that cosecant of theta, is hypotenuse over opposite, because it's the inverse or the reciprocal of sine. So in this triangle, that's my hypotenuse, that's my opposite, and that's my adjacent. So that's how that became that.
Oh, okay.
And the 1/4 was just from the original problem, it still was coming through, so.
Professor, I gotta let you know, my buddy's got a math degree and he told me math's a big circle and he laughed and now I get it. And I'm fucking a little angry.
Now you get it. Yes. Math will, yes, definitely is circular.
Oh, in my mind, I'm just imagining somehow we always end up back at talking about sine, cosine, and tangent, about pi over square or 2 and everything like that. And everything just isn't going to turn to that. I don't know why. It just feels that way.
Yeah, it's because in the essence, there's always those base things that you can make everything back into. So I remember when I was in college, everybody's like, you try to prove things. Like that's like the essence of math is trying to prove things. And we're like, well, why is 2 + 2 = 4? And somebody actually wrote a proof. It was like a 400-page proof proving 2 + 2 = 4. I don't know why he did it. He must have been bored, but they did it.
But what happens when 2 + 2 doesn't equal 4?
It has to. That's he's proven that it actually works that way. That's the one difference between math and science. Once you prove something, as long as there's not a flaw in your proof, it is always true. It'll never be false. That's
So
what
you're saying there's a flaw in the proof that one day all of math could just break apart?
Yes. There actually that actually could happen. If they could find a flaw in the proof, it could literally throw everything into chaos. So here's a great example of this. In Euclidean geometry, there's a statement that when you do a transversal, the alternate interior angle or the alternate interior angles are equal to each other. The converse of it is a triangle has 180 degrees. Right? Everybody learned that in school, a triangle has 180 degrees. Well, one mathematician decided that what if that statement that we're just accepting as fact didn't exist? And they actually created, which is known as hyperbolic geometry, which has a triangle that has 0 degrees of angles. So he created an entire new field of mathematics by not accepting the premise that a triangle is 180 degrees.
How can a triangle have 0 degrees?
It's on a plane, a spherical plane. So if you draw a line on the Earth, you can actually draw 3 lines on the Earth that meet, and the actual lines come together with 0 degrees of angle because it's a sphere. Look it up. It's kind of interesting. If I think about it, I'll pull up the picture for next class. All right, back onto the wonderful, annoying trig substitution. Here's a great example of a problem that looks like you need trig substitution, but you don't. And this is why in every problem I've said, can I do U substitution first? If I had an actual class time where we're sitting in class, I normally make all the students do this problem as I'm walking around looking at them, and then go up to the board and solve it in like less than a minute. Because everybody's like, oh, we're all doing trig substitution. We're doing the trig substitution. And then this problem assumes, oh, I'm going to do trig substitution. And it takes a little while to do it. And you can do this a lot simpler. This is why you always want to look for U substitution. Notice how this one, remember in all the problems so far, I've had x squared. And I said, well, we can't do anything with x squared. Notice how this one just has an x. So if I make U x squared plus 4, du is 2x dx. So that means 1/2 du is x dx. Since I have that, I can do U substitution. Also notice that the x is on top, which makes my life a little bit easier. So this integral becomes 1 over u squared, or the square root of u, du, and I can put the 1/2 in front. So we add 1. So we've got 1/2. We add 1 to that, and we bring out a 2 basically. So it's 2 u to the 1/2. So this whole problem becomes the square root of u, which is the square root of x squared plus 4 plus 3. So in a problem like this, it's really simple to do U substitution. It's really complicated. It's not complicated. It's just, as you saw with the other 2 problems, a lot more work to do it out with the trig substitution. But you could. The trig substitution would still give you the right answer. It's
So you just
again,
look out for a lone x.
Yeah.
So lone x in numerator.
Yep. As long if you have an x in your numerator, do U substitution. Because that's the thing. It's like if you have that piece that you can get rid of in the problem, then U substitution works. If you don't have that piece, then you have to try something else.
That's because we're looking for x dx.
Yep. Because you need the x dx in there. You need that x.
And when we don't have x dx, we need to do something besides U substitution or in addition to it.
Yeah, you have to do something else. That's where the trig substitution comes into play. That's why we have the trig substitution. It's when we can't do a simple U substitution. All right. All right. Two more problems. So first thing, look at this one. I don't have an X, so we're not going to do the X. What's another thing about this problem that looks different?
Ooh, it's not like a square root. It's a cube to the square root cube thing. That
Right. So I have a square root, but the way it's written, I actually have a square root cubed. So yes, that is gonna come into play in my calculations a little bit, but I can modify it so I still have that square root piece in there. And that's the first thing I'm gonna do. One more thing that's different about this problem.
It's a defined integral.
It's a defined integral. So that's actually going to make our lives easier at the end. Because when I have a defined integral, when you're doing any kind of substitution, I can change my the A and the B as I go through the problem, so I do not have to transfer back to the X. So we're not going to have to do the triangle for this problem because I'm going to change them to thetas. And then we can just plug in the thetas instead of having to worry to go back to the X. That makes our lives a little bit easier. So let's do one little change in the problem first so we can actually see the square root. So I have x to the third over square root of 4x squared plus 9 to the third power. So that's what I have there.
Professor, the way that's written, is it 3 times the square root of 3 all over 2?
Oh, yeah, it's 3 squared root of 3 over 2. Yes. Yep, the 2's are under the whole thing. I had to catch which piece you were talking about. So I'll rewrite it real quick so you can. 3 squared root of 3 all over 2. Yeah, that does make a difference. All right, so now we've got our the root, actually in this case. So, or my square root, so I can actually do the calculations with it. So the question is what am I going to make my trig substitution be?
Same as
So what-
2 problems ago, which is the x equals a tan theta, right? But there's that 4, there's that pesky 4 in the way. How do we get rid of that?
All right, so very good. So if the 4 wasn't there, this would just be 3 tangent theta, correct?
Mhm.
Okay, I've got to get rid of the 4, correct? So how would I get, so it's 4 times x squared, right? So how would I get rid of a multiplication?
Divide.
I would divide. Now, whatever I make x, I'm going to square it, correct? So I'm going to divide by 2. So I'm going to make my x 3 tangent theta or 3 over 2 tangent theta. Because when I plug it in, that 2 on the bottom will become a 4, which will get rid of the 4 that I don't want. Does that make sense?
So to get rid of the 4, we divide. And because we're dividing by something that is squared, right? 2 squared is 4. So we put in the 2.
Yep.
But wouldn't we need to divide the 9 by 4 too?
No. So in essence, here's another way you can look at it. This might make a little more sense to the people who are slightly confused. So I've got 2x squared plus 9, right? So in essence, I'm making 2x 3 tangent theta. And then I have to divide both sides by 2. So that's another way to look at it. That 2x is actually what I'm replacing, just like the x on the part. So instead of having just x, it's 2x, which I need to solve for x. So that's how I bring the 2 over. That's why it has nothing to do with the 9 yet. The 9 is still a separate piece. The 9 is helping us get that 3, because that's still technically a squared.
Yeah.
Okay. So it's one of those things that it looks like we can do it. So we try it, but we might have to manipulate it a little bit to make it work. So,
So
and
sir,
whatever-
I'm just curious. In the book, it says we're using like the tangent substitute method. So with this kind, how do we exactly know like when we need to use like the tangent substitute?
that's the table.
All right.
So it's one of those 3 things. Those are the only ways that I can write a square root. So whichever one it comes up, that's the one we're going to use. So in this case, it's the a squared plus, or the x squared plus a squared. That's why I'm using tangent. Okay, so always go back to that table. All right, so now I've got my x. Now we're going to do a little bit more with this. So the first thing I need to do is I still have to find my dx. So my dx is going to be the derivative of this. So it's still going to be, it'll be 3 over 2 secant squared theta d theta. So that's step 1. The next thing I'm going to want to do is I want to take these defined integral or defined parts and change them from x to tangent or to theta. So I'm going to take my problem. So I have x. So in this case, my first one is 0. So 0 equals 3 over 2 tangent x or tangent theta. So 0 equals tangent theta. So what value of theta is going to make that work? And that would be 0. So 0 equals theta. Okay. Does that part there make sense for the 0? So that
This
was
is
that.
SOHCAHTOA, right?
Yeah. So, well, it's not necessarily SOHCAHTOA. This is once you, it's actually the arc cotangent when you're actually solving it on a calculator or whatnot. You're trying to find the value that would give you of theta that would give you 0 on tangent. And when you're looking at the curve on tangent, is when theta is 0.
Hmm.
Let's do one where it's not 0 and it might make might click. So the next one we have is 3 squared of 3 over 2 equals 3 over 2 tangent theta. So this one simplifies down to the square root of 3 equals tangent theta. So actually, where it's going to help you is in pre-calc, if you did, which is one of the things I always do in my pre-calc class, I actually have my students create the unit circle because this is where it comes into play. On the unit circle, what's the theta that's going to give me my tangent of square root of 3? And it actually ends up being theta is pi over 3. So on my unit circle, when I'm looking at it, the value that's the when you can look at in terms of the SOHCAHTOA when you do the triangle, it's going to give you the pi over 3 is going to give you the tangent value of square root of 3. And unfortunately, there's no simple way to do that on the calculator and get the actual pi over 3. If you do it on a calculator, you're going to get it in terms of a decimal.
So could you draw the triangle for us real quick? I think I have it, but I just want to make sure. So the angle of pi over 3 is what you're saying. But let's say we didn't know it was pi over 3, but we're just drawing a triangle.
So, trying to think of the easiest way to do it to get the actual angle. Actually, we'll do it this way. Hold on. Because it's not really a triangle. The triangle is not really going to help you with it. So if we look at the unit circle here. So remember, tangent is, so in this case, my x value is my adjacent and my y value is my opposite. So tangent's going to be the x value or the y value over the x value. No, sorry. Yeah, opposite over adjacent. So I've got square root of 3 over 2 over 1/2. So if we look at it, it's either going to be this one because that one has the square root of 3 in it, or this one. But I want the square root of 3 on top, not on the bottom. And that's going to be the one on top. So the value, if you did the square root of 3 over 2 divided by 1/2, you'd get just square root of 3. So that's going to give you the pi over 3. That makes sense?
Are we able to pull up a quick unit circle on the test?
Like I said, you're going to have, you can make a cheat sheet. So having a cheat sheet, like a sheet of paper, I wouldn't use a ton, but I'm not sitting in your room. So I'm not going to sit there and say, oh, if you have 2 sheets, it's bad. You want to try to limit it down as much as possible because you don't want to have to be constantly flipping through things. So yes, I'd probably have a unit circle on it, especially considering we're going to need it to do some of those basic trig functions. So, and if I was going to do it, notice the unit circle doesn't have my tangents calculated on it. I would go through and calculate my tangents next to it. So I have that value of tangent as well. Because you're going to have the sine, you're going to have the cosine. Having the tangents would also be very helpful.
Why did we want to evaluate this now before we finish doing integration?
Ah, good question. Because if I do it afterwards, I have to, if I don't do this now, I have to go back to X and then plug these numbers into the problem to get the answer. By doing this now, I don't have to go back to X. So I'll be able to plug in 0 and pi over 3 into theta. It saves the triangle step at the very end. And it saves you having to do the calculations with 3 squared and 3 over 2. So it just makes the problem simpler to work with in the long run. I'm just rewriting the problem and then we're going to actually go through and plug everything in. So this whole problem becomes all right, so I've got that. Remember, X was the tangent theta. So I've got, so my, now notice how 0 stayed 0, but the 3 squared became pi over 3. So I've got 3 over 2 tangent theta to the 3rd power over the square root of 3 over 2 tangent theta squared plus 9 all raised to the third power. And then rehab secant squared theta d theta.
Professor, why don't we have the 4 there still again? Dumb question, probably, but
Nope, not a dumb question. I forgot the first. So very
please
good.
go. The 4 is supposed to be there.
Yes, very good question. The 4 was always there. She just didn't see it. Yes, you have to make the 4 there too, because we're going to get rid of it in the next step. So, all right.
Which, oh, yeah.
Huh?
No, thank you.
All right. So now we got to take this messy problem and simplify it down. So this piece in here, the more you work with it, the better you're going to get at figuring out where things break down and simplify down. Remember, the entire part of doing the 3/2 was to get rid of that 4. So let's we can kind of ignore the 4 because we know it's going to be gone. So this becomes 9 tangent squared theta plus 1. So it's 9 secant squared theta. So it's 3 secant theta. So we've got this top part becomes 27/9, tangent to the third theta. Actually, oh, not 20. Wait, how do I get 9? That's not 27/8 over 27 secant to the third theta times 3/2 secant squared theta d theta. All right. So everybody see how I got to that step?
Now I lost the 4.
The 4 is gone. The 4. So the 4, if we looked over here, when we did that 3/2 squared, that becomes 9/4, which cancels out the 4.
Okay.
So that was literally why that was where I got a step ahead of myself when I wrote the 3/2. Is because the 2 literally is going to cancel out that 4, so it's gone immediately. Okay, let's clean this mess up over here. The 27 and the 27 are going to cancel each other out. So I end up with 3/16.
Wait, before we do that, Professor,
Yeah.
quick question. So, if the whole thing was raised to the power of 3/2 on the denominator there,
Yep.
how did we get, I'm stuck at 9 times secant squared theta to the power of 3/2.
So you're stuck at, hold on. You're stuck at
Oh, I
this part?
see. Oh, so what you're saying is if I just think of it as a square root, then I can make it 3 times secant theta and then raise that to the
Yes,
to the third power.
yes. Because remember that a fractional exponent, the top is just a power. The bottom is a root. So since this one was 2, that's where the square root came from.
Got it.
All right, so I have tangent to the third theta over secant theta d theta. All right. Everybody see the simplification down?
I mean, we can make it sine 3 theta over cosine squared theta.
Yes, that's my next step. Very good. That is literally my next step. I just wanted to make sure everybody could see how I got this big mess down to that little problem.
So I'm doing it while you're doing it, and then I get there and I'm still confused how I get there sometimes.
That's fine. So yeah, the 27s cancel out. So I'm left with 1/8 times 3 over 2. That's where the 3/16 came from. And just pulled that out front so I didn't have to worry about it. And then the secant squared canceled out to the secants down the bottom. So
You know, watching you do these, it like makes so much sense, but I can't imagine a world where I figure these out on my own.
and that's so you'll get there. It's a lot of times when we're doing these problems and I'm going through them, it's like I'm just giving you the strategies and the pieces to be able to break down the problems that you need to work with. So the nice thing about the way math books are set up, all the practice problems at the end of it are practicing this one skill. The key and the thing that you're going to have on the test, which is going to be so important, is looking at a problem and figuring out which strategy you're going to need to use. That's actually going to be the hardest part of this test, is figuring out, okay, this one I need to do substitution. This one I need to do trig substitution, because they're not going to be in order and told you use this function or use this setup for it. That's the hard part. So that just comes with practice, is being able to identify the little pieces of like, okay, I need to do this. And then it's working through that process once you have it. And that's just a set. That's just like a recipe, like cooking. It's like, once you have it, it's like, here's the steps that you're going to go through and do it. So it's not easy. It took me a while to be able to figure out how to explain this well enough for people to actually get it. So it's like, as with everything, it takes practice, but you'll get there. You really will. All right, so let me just rewrite this part because we're going to have to do some more. We're not done, unfortunately, because I haven't even actually done the integral yet. All right. So again, I got tangents and secants. This is not going to be easy to work with. So let's change this to sines and cosines because those are nicer. And when I have sines and cosines, I might actually be able to work out with u substitution. So tangent is sine to the third over cosine to the third. Secant is cosine theta. So that's how that becomes that. All right. Okay. Now that we've got sines and cosines, I can do a little bit of simplification of this down just some, because when I'm going to do my u substitution, I need to get everything. Remember back we did our last class is I need to have something that I can change, but all the rest of the stuff has to be in one. So right now, when I have sine to the third theta and cosine squared theta, the u substitution won't work really well because I have sines and cosines, and only one part's going to disappear. So I'm going to change this problem a little bit. I'm going to change this to 1 minus cosine squared theta over cosine squared theta. And this is my extra sign. So I took two of those signs and made 1 minus cosine squared theta. Because now I have everything in terms of cosine, and my sign is going to disappear when I do my u substitution. So now I can make u cosine theta in du is negative sine theta d theta. Does that part make sense? This is where those, okay, I'm stuck. Like when you get this whole page is an, okay, I'm stuck. When you're at this point right here, it's like, okay, I can't do this. What's a strategy that'll help me figure that out? Well, changing things to sines and cosines. And then we're at this point. It's like, okay, everything's in terms of sines and cosines. Now I might be able to do substitution because sines and cosines work really well, but I have a whole bunch of extra signs. What do I do next? It's like, think back to that Pythagorean identity. It's like, okay, let's see if I take, that's two of them. So I can take this and say that's sine squared times sine. So now I have that sine squared that can change to that. Now you're at the point of this one. It's like, okay, now I've kind of got this organized. Let's look at u substitution. So again, anytime you get stuck, it's like take a step back and say, okay, what strategies do I have to be able to simplify this down a little bit more? Because obviously there's got to be a way to break it down more. And that might be, I can't figure it out, and I snap a picture and send it to Mr. Baker and say, okay, I'm stuck. I need some help figuring out how to get past this point. And I send you back a message if you're stuck at the green one goes, change everything to sines and cosines. Start there. So I won't tell you the next step, but I'll give you that piece to get to the next step. I'll get you unstuck. So it's like those little things. And the more you do them, those little things are the things that are going to become second nature to you. And you're going to remember how to do it. So. All right. I can't remember who asked at the beginning, asked, why did I change things to 0 and pi over 3? Because I had it in the other terms, and I said I didn't want to go back to the x. This is, see, I remembered how to do the whole problem, so I knew where I was going. I now have things in terms of u. So if I had to change things back to x, I would have had to do 2 changes back, which we did in one of the other problems, which is a lot of work. In this problem, since I'm changing to u now, I can actually change my whole thing to u and not even have to worry about going back to theta, which kind of is a nice thing. So the first one is u is cosine of 0. So if cosine is 0, what's u going to be?
Yeah, but
1.
Yeah, that's 1. And then cosine of pi over 3, if we go back to my unit circle, cosine is 1/2. So this whole problem becomes 1 and 1/2. And I have 1 minus u squared over u squared du.
We have to add the negative in there, right? Or am I missing that?
Oh, you're right. I forgot the negatives. You're right. So that's going to be negative 3 over 16. I forgot to bring the negatives by the way. All right. So so right now I have 1 to 1/2. Not really the way we want to do things. So if I was to switch those, so I'm going to do 1/2 down the bottom and 1 up top. It just changes the sign. So now it's going to become positive 3 over 16. And then I have u to the negative 2 minus 1 du.
So we're allowed to change the definitions of the integral as long as we flip the sign?
Yeah, you can flip them. You can flip them back and forth as long as you switch the sign.
Is that in any case?
Yep.
But what happened to the denominator there?
Oh, I simplified it. So if it's in the denominator, I can put it under each one. So this became 1 over u squared minus 1. Or actually, minus, rewrite this one. U squared over u squared, which became that. And I moved up the, I made it u to the -2, so this way I can just do the power rule.
Wait, look, wait, what? So we
So-
switched the signs, and then it's, oh, okay, so to the negative, so she moved it up. Okay.
Yeah,
got it.
I just changed it to a -2. All right. Okay, any other questions with that?
Are we gonna finish it?
Yeah, we're not done. All right. So I did the integral of each piece. So I have -1 over u minus u. And I'm evaluating that from 1/2 to 1. So I have 3 over 16. If I plug in the 1, I get -1 minus 1 minus -2 minus 1/2. So I get -2 plus 2 plus 1/2 equals 3 over 32. And that's the answer. That was why we didn't want to go all the way back to the x's.
And how many of these problems per test?
532. So in in 7.1, we did it was the integration by parts. And remember how whenever you have an x to raise to a power, if it was like x to the third, you had to do it a couple times to break it down. So when I was making my test for the first time I taught this class, normally I take problems that we've done and I just change numbers in it. Well, I took one of the problems and I changed it from x to the third to x to the fifth. Little simple change. Yeah, it made you have to do 5 integration by parts. So the problem, like the one kid did it, it took him like a half hour to do the problem. And I'm like, oh, this is a problem. So no, I don't typically, like when I'm going through and doing a test out now, after I make those little stupid mistakes, I typically do the test. And if it take, like for you guys, you have about an hour and a half to do your test because you have from 5 to 6:40. If I can't do the test in about 20 minutes, it's too long. So I would cut stuff out of it. So because that's basically giving you like 4 times the amount of time to do the questions that I would be able to do. And when I do them the exact same way that I would have you do them. I write everything out. So it's not like I'm saying, oh, hey, I know this answer and just writing down the answer. I'm going through and doing out the entire process. So I think your test for this one is 10 questions, but they're not all this long. So it's not, it'll take you about the hour and a half to do it. So it's not going to be too bad. And I should have, my goal is to do the practice test tomorrow afternoon. So that should be up. Does that alleviate some of your fears?
Slightly.
Will we have a test prep session before the test? Like, when is the
Yeah.
first test?
Yeah, so I'm gonna create the practice test tomorrow afternoon as long as I don't get stuck into a meeting. In worst case, I'll just do it when I come home. So I will do the practice test up tomorrow afternoon. So you'll have access to that, and I'll post a thing on the my website saying that that's available. Next Tuesday, so tomorrow or Thursday's class, we're gonna go over the last process, which is partial fractions, which sounds really complicated, and I'm gonna try to make it as easy as I can. That'll be the last strategy we're going to do. Next Tuesday's class is basically a review for your test. We're going to go through section 7.5, which is how to pick which method it is. And then we're going to do some of the problems in the practice test. So that'll basically be the review for the test. And then next Thursday will be your test. So yeah, we always have a review day before the test.
So next Thursday is our test.
Next Thursday would be your test, yes.
Each test comprises